Yes, sir.
Yeah. So today we'll discuss about. So we completed with all the modeling styles. That is switch level modeling, gate level modeling, data flow modeling, and behavioral modeling. Today we are going to start about the test bench. Okay, how to write the test bench for the Verilog code. Okay, test bench. So just to go through the recording sessions and all those things. So today we'll start it about the test bench. Okay. So test bench of today we'll discuss combinational circuit. Okay. If time permits, we'll see a sequential circuit also. Combinational circuits we'll see. Okay. Uh, so what are the combinational circuits you studied? Can anyone say? Can anyone say? Half adder, full adder. Next, tell me. Half subtractor, full subtractor, and next ripple carry adder and carry looked adder, and you have advanced adders. Okay, carry save adder and all those things. Advanced adders. Okay, that will be included in the project. Okay, and you will study about multiplexers. In the multiplexers, you studied about 2 cross 1 mux, 4 cross 1 mux. Okay, and next dmux, dmux, dmux. You have 1 cross 4 dmux and 1 cross 8 dmux. Okay, and next you have encoders, encoders 4 is to 2 encoder and 8 is to 3 encoder. Okay, and next decoder, decoder 2 is to 4 decoder, and next you are going to study about 3 is to 8 decoder and code converters, code converters. So what are the code converters? You will study about BCD to decimal, BCD to decimal, and binary to gray, binary to gray, and gray to binary, gray to binary. Okay, and next comparators also, comparators, comparators. We study about 1 bit comparator and 2 bit comparator. Encoders, somebody unmuted. Please mute. So priority encoder. You will study about priority encoder. Okay. So this in the encoder, you will study about the priority encoder. Okay. Priority encoder. So these are the combinational circuits. No. So in the digital, you are going to study about these combinational circuits. No. Is it fine?
Yes, sir. Yes, sir.
Yeah. Yeah. So test bench. Test bench. Okay. So test bench is nothing but we are going to generate the stimulus and provide it to the design and check the outputs. Okay. So what is test bench? Uh, we are uh, we are going to generate the stimulus. Means we are generating the test cases. That means we are going to generate the stimulus. Okay. Stimulus. That is nothing but we are driving the values. Okay. Design will sample the values. Okay, and provide it to design. Okay, provide it to design, and we are design will process, and we are checking the outputs. Okay, we'll check for the output. Okay, check the outputs. Okay, so that is nothing but test bench. Okay, So that means here this is test bench. This is my TB test bench. Okay. So that means here you wrote the code for half adder or full adder, any combinational circuit. In the digital, what you did, you verified that circuit is correct or not with the truth table, and you drawn the K map, and from the K map you got the logic expression. From the logic expression, you drawn the logic diagram. Here you are writing the design. So how to verify your design is correct or not? Okay. So by using the test bench only, we are going to write the to verify that your circuit is working properly or not. Okay, that is nothing but test bench. Okay, so this is your design. This is your design. Okay, and through the test bench, you are giving the stimulus. Through the test bench, you are giving the stimulus, and these are the input for the design, and you are getting the output from the design, and from that you are seeing the output through the test bench. Okay, output through the test bench. Okay, is it fine? What is test bench and why we are using? For each and every design, we need to verify whether this design is working properly or not. So in order to verify that circuit, for each and every code, you need to write the test bench for verifying that circuit. Is it fine? Shall I move forward? Okay. Shall I move forward?
Yes, sir.
So next,
Yes, sir.
first, I am writing the half adder circuit. Okay. I am writing the code for half adder circuit using behavioral modeling. Okay. So behavioral modeling, I told you, like Verilog code will start with module. And what is my module name? Half underscore adder. Okay, half underscore adder. And I am declaring the input. Okay, input a underscore ha. Okay, a underscore ha, comma b underscore ha, comma mm, uh, comma. So two inputs and two outputs. No output. So output is which data type? I need to declare with reg data type. Why? Because when you use the data flow modeling, you need to declare the I told you the port rule connections. Okay, so you need to declare with reg data type sum underscore ha and cout underscore ha cout underscore ha. Okay, I am writing always at the rate sensitivity list. I am giving star. Okay, this is nothing but implication operator. I already told. And multiple statements are there means you need to write between the begin and end. Okay, so begin sum underscore ha equal to what? A underscore ha XOR operation of b underscore ha. Okay, and carry out underscore ha, that is equal to a underscore ha XOR operation of b underscore ha. Okay, end and end module. So every begin should have the end and end module. Okay, this is a simple code for half adder circuit. Half adder we already seen. So it consists of two inputs. So one is a underscore ha and b underscore ha, and this is half adder circuit. And you have two outputs, sum underscore ha and cout underscore ha. Is it fine? Do you understood this design? Simple half adder code. Shall I move forward? Waiting for your response.
Yes.
Okay. Okay. So next, you need to write the test bench. Okay, I need to write the test bench for this. Okay, test bench for the combinational circuit. So like uh, so here there are only four steps are there. That steps I will tell you. Module. Test bench also start with module. Half underscore adder underscore tb. Okay, half underscore adder underscore tb, and you are no need to declare the inputs and outputs. Why? Because outside this bracket you need to declare the internal variables. Okay, so here in the module what you did, in the module within the bracket you declare the input and outputs, no? So in the test bench we need to declare the internal variables. Okay, so so internal variables means here input for the test bench, that is I need to declare as a reg data type b underscore tv. These are not input, these are internal variables you need to declare. Okay, where sum underscore tb comma cout underscore tb. Okay, cout underscore tb. Okay, so this is nothing but step 1. What is step 1? You need to declare the internal variables. You need to declare the internal variables. Internal variables. Okay, so you need to declare the internal variables. Step 2. Step 2. So what is step 2? You need to instantiate the design in the test bench. Okay, you wrote the design, no? So that design you need to instantiate. Okay, so instantiate the design in the test bench. So we already seen the instantiation, no? Can anyone unmute yourself and tell me how many types of instantiations are there? Can anyone say? Hello. In the instantiation, I told you there are two types of instantiation are there. One is connection by name and one is connection by position with order list. Okay, so connection by name means you have like design name and in the bracket test bench variables you will get. Okay, design variables and outside the bracket design variables will come, and inside the bracket test bench variables will come. Okay, so here connection by position means how you declare the input and output, that same position you need to follow. Okay, so see here, suppose half underscore adder. This is my design name, no? Here I wrote the design name half underscore adder and instance name. What is the instance name? HA, and I need to declare how you declared first A underscore TB. So A underscore HA, B underscore HA. Here I declared the inputs, no? The same order I need to follow. Okay, that is nothing but connection by position with order list. Okay, so A underscore TB comma B underscore TB comma sum underscore tb comma cout underscore tb. Okay, so this is nothing but what connection by position with order list. Connection by position. Connection by position with order list. Order list. If it is connection by name, how you to write half underscore adder instance name. Instance name is optional. You can use UUT, DUT, or HA, anything you can use. Okay. Outside the bracket are nothing but design variables. Okay. So that is A underscore dot. You will get dot. Okay. Dot A underscore HA and A underscore TB. Okay. Comma dot B underscore HA, B underscore HA in the bracket B underscore TB. Okay, like this you will get dot sum underscore HA and sum underscore TB. Okay, comma cout underscore HA dot you will get. Okay, dot will get. Okay, so connection by name means you will get dot. Okay, cout underscore TB. Cout underscore TB. So this is nothing but connection by name. Connection by name. So mostly in the industry they will use connection by name only, not connection by position. Up to here, do you understood? Step 1 is declaring the internal variable. Step 2 is nothing but instantiating the design in the test bench. Is it fine? Shall I move forward?
This connection by names are, can I change the position or no? there also
No,
I have to follow that.
I can change the position. Why? Because names are there, no?
Okay.
I can change the positions. But here, whatever this you need to remember. That means the variables outside the bracket are nothing but design inputs and outputs. The variables inside the brackets are nothing but test bench internal variables.
Okay.
But position is you need to follow how you declare the input and output. That same position you need to follow. Is it fine? Shall I move forward?
Yes.
Yeah. Next is step 3. Step 3. Okay, what is step 3 means? Initialize the reg variables. Initialize the reg variables. Okay, so initial begin begin. I am using concatenation operator. What are the reg variables? A underscore tb and b underscore tb. Okay, so reg variables are a underscore tb comma b underscore tb. I am declaring with 0 end. Okay, this is step 3. Step 3 means initialize the reg variables. Initialize the reg variables. Okay, and step 4 driving the inputs for the design, giving the stimulus, driving the input for the design, okay, how you are driving the inputs? I need to start with initial. Okay, as I told you, like initial is non-synthesizable. We can't convert into hardware. That's why we are using initial in the test bench. Okay, so when you are using in the design, you should not use initial. You should use always. Always is synthesizable. Okay, so in the design wherever, so I didn't use any initial. So I'm not used any initial. I used always only. Okay, so that you need to remember. Okay, which are synthesizable constructs and what are non-synthesizable constructs means. So you need to remember that. Okay, and begin multiple statements are begin a underscore tb that is equal to 1 tick binary 0 and b underscore tb that is equal to 1 tick binary 0. Okay, you know the truth table for the half adder circuit we already seen in the digital sum and carry. So 0 0 0 1 1 0 1 1. Okay, sum 0 carry 0, sum 1 carry 0, sum 1 carry 0, sum 0 carry 1. Okay, uh, and next I am giving a delay after 10 time minutes. After 10 time minutes, a underscore tb that is equal to 1 tick binary 0 and b underscore tb that is equal to 1 tick binary 1. Okay, and next next I'm giving here, this is the continuation after 10 time minutes. This is nothing but simulation time means 10 time minutes I am giving. Okay, and so a underscore tb that is equal to 1 tick binary 1 1 tick binary 1, b underscore tb that is equal to 1 tick binary 0. Okay, after that as 10 a underscore tb that is equal to 1 tick binary 1 and b underscore tb that is equal to 1 tick binary 1 and end module. Did you understood the test bench? Is it fine?
Sir, how did you determine this 10 number? Can I put 1?
One also you can take. One also. That is simulation time. 10 also, 1 also. Within that, like if you are not using this delay means you can't see the outputs. I will show in the tool. If you are not giving this delay means I can't see the this waveforms. Within the every delay, there is like precision and time scale will be there. Okay, precision and time scale. So the time scale I am giving nanoseconds means this is in terms of 10 nanoseconds.
Okay.
Okay, is it fine? Did you understood this?
Yes.
Okay. I'll show in the coding. 1 second. This is half-adder data flow modeling. Okay. So here half-adder DUT is there. So DUT means here you are using see here. Uh, so just this is data flow modeling. Module half underscore adder half DUT input a comma b output sum comma carry. For data flow modeling, you are using continuous assignment statement. No, assign sum equal to a x or b, assigns carry equal to a and b, and end module. Okay, this is my design. And coming to the test bench, this is my test bench. 1 second. This is half underscore TB is not there. 1 second. 1 second. That is corrected. 1 second. Half underscore DUT I told. This is TB. See here. Uh, half so module half underscore TB. So we need to declare the reg variables, the internal variables. So where sum comma CA, reg a comma b, and half underscore DUT TB a comma b comma sum comma CA, initial begin, dollar display. So dollar display is the system task. It will display the a, b, and sum and carry. So I am giving a equal to 1 tick binary 0 and b equal to 1 tick binary 0. After 10 time minutes, I am giving a equal to 1 tick binary 0 and b equal to 1 tick binary 1. And dollar monitor. Dollar monitor means what? If there any change in these variables, it will display. Okay. If there any change in this either a, b, or sum or carry, it will display. That is nothing but always it will monitor the signals. Okay. As 10 a equal to 1 tick binary 1, 1 tick binary 0. Okay. Dollar strobe. Dollar strobe means what? Dollar strobe will display last updated values. Okay. Dollar strobe will display last updated values. Hash 10 a equal to 1 tick binary 1, b equal to 1 tick binary 1. Dollar display a equal to this percentage b sum equal to percentage b. And a comma b comma sum comma carry. I need to execute for 50 time units, 50 nanoseconds. Dollar finish is nothing but I need to finish the simulation. Okay. So to finish the simulation, I am using the system task like dollar finish. Suppose if it is dollar stop means I can pause the simulation. Okay. End and end module. Okay. Is this test bench is fine? Is this test bench is fine? Design and test bench is fine.
Yes.
Okay. So here this one you can execute in the EDA playground or you can execute in the Vivado also. Okay. So suppose if it is EDA playground, just open the EDA playground. So log in with your email. So log in with your email. So here you need to write the code. Here you need to write the test bench. Okay. So here this is my code. So select all, copy, and here I am pasting. And test bench also select all, copy, and here I am pasting. Here I am pasting. Okay. So tools and simulators. I need to click Aldec Rivera. Language is system Verilog or Verilog. Okay. So run this code. Just click on run. See here. First initially the reg variables are x only. No. So it will execute a equal to x, b equal to x, and c equal to x. And a equal to 0, b equal to 1, sum equal to 1, carry equal to 0. Okay. And a equal to 1, b equal to 0. First I given a equal to 1, b equal to 0. No. and A equal to 1, B equal to 0, sum 1 carry 0, A equal to 1, B equal to 0, sum 1 carry 0, A equal to 1, B equal to 1, sum 1 carry 0, sum 0 carry 1 you need to get, okay. This last updated value, this value, A equal to 1, B equal to 1, sum 0 carry 1 we are getting. So this one I can execute in the Vivado also. So just open the Vivado. Just it will take time. Just will wait. So in the EDA playground, you can see the EP waveform also. Suppose here open EP waveform and select tools and simulators as ICARS Verilog. Run this code. Open EP waveform means it will run. VCD. Some VCD files are missing. We need to add the VCD files. Okay. In the test bench, we need to add the VCD files. That's why we are not getting. So in the Vivado, what you need to do? Go to project, new project, next, and you need to select the path. Okay. I'm selecting the path. So here RTL. One second. RTL. My digital and Verilog. Mm, RTL weekend batch. Okay. Uh, select weekend batch, and I'm creating a folder on training and development. My RTL weekend batch. Here I'm selecting a folder. So RTL codes using Xilinx Vivado. Okay. So I'm created the folder. So again browse this. So here in this I'm selecting this folder. Okay. So whatever the programs are there, that will be stored, and I'm creating the project with what means combinational circuits. Combinational circuits. Okay. Like this, you need to create the folder and you need to remember the path. Next, so my project is RTL. Next, create the file. Okay. So my file name is half adder. Okay. Half underscore adder. Okay. And my file type is Verilog only. And choose the location means same location I'm choosing. Select. Okay. Next. This constraint is optional only. I'm clicking on next, and it will select the FPGA folder, FPGA file. By default, this is the part number of the FPGA. So these are the uh, means features. Okay, features of these are how many IO pins are there, LUT elements, flip flops, programs, all those things. It will show. Click on next and finish. My RTL project will be created. Okay. So my module name is also same. Yes. Click on this. Okay. So copy this code. One second. Copy. Select all. Copy. And here this is the time scale. 1 nanoseconds by 1 picoseconds is nothing but what wherever I am giving the delay, that is nothing but one. It will take in terms of nanoseconds. Picoseconds means this is the precision. Suppose if you are getting the decimal values, it will be round up to nearest value. Suppose if you are getting 10.54 like that, it is getting. or 9.56 like this it is getting, means it will round up to 10 nanoseconds. Okay, so this is the precision. Okay, there are some calculations are there to find out the precision and all those things. So copy here, paste here, and this is the design source. So you can see the design also. Last class I told you know how to see the elaborate design like that. So if you want, you can see, save this file, elaborate the design. So the design will means this tool is converting your code into gate level netlist by using data flow modeling. Syntax error. One second. Yeah. Half underscore dut is there, no? Okay. Half underscore. Here I am giving adder. Okay. Half underscore adder. This is half underscore dut, no? Yeah. That's why it's coming. Save this file. Yeah. Now we will get a Z only. So close the simulation. So elaborate the design. So you got the half adder circuit. XOR gate followed by AND gate. Okay, XOR gate followed by AND gate. Okay. So suppose next if you want to write the test bench, go to simulation sources. Okay, create the simulation sources. So Marty, what is my simulation file? Half underscore TB. No. So this module name I need to give. Okay. So copy this and here create the file. Paste this where I need to see store same thing. RTL codes. Okay, finish. My module name is also same, half underscore TB. Next here half underscore TB is there, no? So this code is there, no? This code. So I need to select all, copy this and paste here, paste here. And my instantiation is nothing but half underscore adder, half underscore adder. So make sure that this design name and this instantiation name should be same. Okay. So otherwise you will getting compilation error. Syntax error. Where you got the syntax error? 1 second. Okay, one more end module is there. Yeah. Yeah, 1 second. It will take time. Yeah. So now see here in the test bench half underscore adder. This instance is created. Okay, TB half underscore adder. This instance is created. So go to simulation, run behavioral simulation. Run behavioral simulation. So go to the waveforms, fit to page. See here. So I gave 10 nanoseconds, no? So here you see A equal to 0, A equal to 0, B equal to 0, sum equal to 0, carry equal to 0. A equal to 1, A equal to 0, B equal to 1, sum equal to 1, carry equal to 0. And A equal to 1, B equal to 0, sum equal to 1, carry equal to 0. And A equal to 1, B equal to 1, sum equal to 0, carry equal to 0. So with the waveforms I can see, or otherwise you can see in the TCL console also. See here, A equal to 0, B equal to 0, sum equal to 1, carry equal to 0, A equal to 1, B equal to 0, sum 1, carry 0, A equal to 1, B equal to 1, sum 1, carry 0. Okay, like that. We can see in the TCL console. Did you understood how I am writing the code and how I am? Is it fine? Shall I move forward?
Yes.
Waiting for your response.
Yeah.
Okay. What about others?
Yes, sir.
Okay. Yeah. Next is one second. Next is full adder. Okay, this is the full adder circuit. Okay. Logic gates also. See here. Logic gates. Logic gates also I can write. Okay. So all gates. This is the code for all gates. Okay. So if you see this code for all gates, module TB, reg A comma B, wire 6 down to 0. So 6 down to 0 means, yeah, this is TB. Sorry, this is TB. This is DUT. Okay. So this is my design file. Okay. All gates. See here, module all gates A comma B comma Y, input A comma B, and output 6 down to 0. So I am using a vector concept. No, how many inputs are there? How many outputs are there? With output, I am giving 6 down to 0. How many outputs are there? Can anyone say? 7 outputs are there, no? 6 down to 0. Okay. Y0, Y1, Y2, Y3, Y4, Y5, Y6. Okay. I am using continuous assignment statement. Assign Y of 0 equal to A and B. Y of 1 equal to A or B. Y of 2 equal to not of A and B. NAND gate. Y of 3 equal to not of A or B. That is NOR gate. Y of 4 equal to not of B. Y of 5 equal to not of A XOR B. XNOR. And Y of 6 equal to A XRB and end module. Okay, this is my design. Okay, and next coming to the test bench, this off adder I will close. Yeah, see here, module TB. I need to declare the internal variables. Okay, so reg A comma B. I need to declare A with the reg data type. I need to declare the this Y with the wire data type. Okay, reverse. Okay, so initially by default I am not declared any data types, means that is wide data type only. In the design, I am not declared any data type. That is, it will take as wide data type only. Okay, as I told you, like in the data flow modeling, we need to use only wire data type. Okay, and next I need to instantiate. Okay, what is my design name? All gates, and name of the instance is insta, and this is what can anyone say? Connection by name or connection by position? Instantiation.
By name.
Connection by name. Okay, so connection by name means whatever the variables outside the bracket are design inputs and outputs. Whatever the variables inside the brackets are nothing but test bench variables. And initial begin, so a equal to so I need to declare the, I need to initialize the reg variables. Okay, initial begin a equal to 1 tick binary 0, b equal to 1 tick binary 0, and initial begin dollar monitor. Dollar monitor means it will display if there any change in the inputs and outputs. Okay, so that means this will be displayed in the postpone region. Okay, we already seen the Verilog event scheduler, no? But dollar monitor and dollar strobe will be executed in postpone region. So that means if there any change in the inputs and outputs, okay, within this variable, it will display. Okay, so I am giving 1 1, and after 15 time minutes I am giving 1 0. After 15 time minutes I am giving 0 1. After 15 time 20 time minutes I am giving 0 0, and hash 50 dollar stop. I need to pause. I can use dollar finish also, nothing will happen. So this one I want to execute. Okay, so this design is there, no? Just once this design name, I'm copy this. Within this, go to the sources, add the design source. Next, create the file name, give the module name, all gates, finish, all gates, yes. Now it is created, okay. So I want to see the design means I need to right click, I need to make set as top, and open this, and this design file, select all, copy this, and paste in this, okay, paste in this, and next I want to go to the simulation sources. So save this file, okay, just save this file, and next go to the simulation sources. So what is my test bench file module? uh, so in order to remember, I am giving all gates underscore tb, okay. In order to remember this test bench, I am using all gates underscore tb, and this design name should be there. Select all, so save all, select all, copy this, and first I want to select this module name, copy this, and go to the simulation sources, add the simulation sources, create file, all gates, choose the file, and select OK, finish, all gates underscore tb, yes. Now my tb file is created. See here, my tb file is created, okay. So go to the tb file, select all, copy, and just paste here, okay. And module, delete this, save this file. Now you see, so in the test bench file, instantiation is created. All and all gates instantiation is created, okay. So I want to see the simulation. So this is in top module, half underscore tb is my top module. So right click, set as top, okay. Right click, set as top, and I want to see the design, elaborate the design. Okay, this is my elaborated design, okay. A and B are the inputs. You have inverter and buffer, and XOR gate, AND gate, NOR gate, OR gate, NOR gate, all gates. The tool is converted into hardware, okay. So close this, and run simulation, run behavioral simulation. So simulation is open, fit to page, yeah, fit to page. Here you see. So just you can zoom this, yeah, yeah, see here. So what is y6, what is y0, what is y0 in my code? AND gate, okay. AND gate, you see y0, both are 0 0, the output is 0, okay. Both are uh, 1 1 means the output is 1, and both are 1 0, 1 0 means the output is 0, okay. 0 1 also the output is 0, 0 0 means the output is 0, okay. That is y0. And what is y1? AR gate, ARB, no. ARB means y1, you see. So both are 0 0 means the output is 0, and see this one y1. Both are 1 1 means the output is 1, and 1 0 means output is 1, 0 1 means output is 1, 0 0 means output is 0. Like this you can see remaining gates like what we have seen like NOR gate, XNOR gate, NOT gate, and XOR gate, XNOR gate, and XOR gate. Is it fine? Did you understood how I am analyzing and the waveform? Do you understood? Waiting for your response.
Yes, sir. Understood.
Understood? Okay. Okay. So I will share these codes just to practice this. Anyway, like full ladder also you can try, and full ladder. This is multiplexer. Okay, multiplexer code. Okay. So multiplexer, you know, like 2 cross 1 multiplexer and 2 cross 1 multiplexer test bench. Okay. So see here, I am using data flow modeling only. You try with the behavioral modeling. For data flow behavioral modeling, the code is same only, but you need to take care of this instantiation. That is, design is there now. Whatever your design and whatever you are instantiating in the test bench, that both design should match. Okay. So see here, I'm using 2 cross 1 mux module mux DUT 2 cross 1. So how many inputs are there? A comma B, S comma S1 comma Y. Input A comma B comma S1. Output is Y. That is it will take as a wire data type only. I'm using assign statement and I'm using ternary operator. Okay, or conditional operator. So that is Y if S1 which is connected B or A. Okay, so that means did you understood or not? That means here I am using the statement. This means this is the 2 cross 1 mux. Okay, this is the 2 cross 1 mux. This is nothing but 2 cross 1 mux. Okay, 2 cross 1 mux we already discussed. Two inputs are there and one output is there and one selection line is there. Okay, so this is S1 and inputs are A and B. Okay, at a time any one of the input is connected to output. Okay, so I'm using the continuous assignment statement, that is assign. Okay, assign y equal to what? If it is S1. Okay, so that means if S1 equal to 1. Okay, which one is connected? B is connected. B is connected. Else, that means y equal to B. Okay, else y equal to A. Okay, else y equal to A. So this is the ternary operator. Okay, we already seen the ternary operator. So within the one statement, I am writing the logic for 2 cross 1 mux. Okay, end. Okay, this is my design. And coming to the test bench, for all the combinational circuits, the test bench is 4 steps only. First, you need to declare the internal variables. You need to instantiate the design in the test bench, and you need to clear the edge variables, and you need to give the driving value. That is, you need to drive the stimulus. Okay. So module, what is my test bench name? Module underscore test 2 cross 1. Reg A comma B comma S1. Wire Y. Mux underscore DUT 2 cross 1. This is my design name. And what is my instance name? Insta A comma B comma S1 comma Y. Initial begin dollar monitor. So dollar monitor means what? It will monitor the signals. If there any change in the signals, then it will display. Okay. So dollar monitor A equal to percentage B. Percentage B is nothing but format specifier. Okay. So 0B means what? 0B means without any space it will display. Okay. That's the use of 0B. So you are displaying in terms of binary means that is percentage B. When you are displaying in terms of decimal means percentage D. When you are displaying in terms of hexadecimal means percentage H, like that. This is format specifier. A comma B comma S1 comma Y. I am giving the stimulus. Okay, A comma B A equal to 0, B equal to 1, and S1 equal to 0. So that is S1 equal to 0 means output is connected to A. Okay, and after that S1 equal to 1 I am giving. Okay, so output is connected to B. Okay, I am giving the stimulus. Okay. So 100 time minutes I am running. After that, I am stopping the simulation. Okay. So this one, if I want to execute, so come out from the simulation. Did you understood the Mux code? Shall I run in the Vivado, or any clarifications is required? Hello. Shall I move forward? So first, you need to select this design source, copy this, and go to simulation design sources. Select design sources. Next, create design source. Select OK. Finish. OK. Yes. Okay. And this is mux dut. Copy this file. Select all. Copy and paste in the Vivado. Paste in the Vivado. So save this file. Save this file. And so we need to set as top module, and next TB testbench file. Testbench is mux this one. Copy this and go to the simulation sources. Create simulation sources. Create file. Create location. Same location I am keeping. Select OK. Finish. OK. Yes. I created the testbench file. Okay. I created the testbench file. What is my testbench file? This is the test. Okay. Test, and next select all, copy, and paste. Okay. So save this file. Okay. So if you want to see the elaborated design, and just to go to this, you need to set as top module. Set as top module. Okay. Open elaborated design. So this is my mux. Okay. A, B, and selection line S1. Okay. So when S1 equal to 0, which is connected, A is connected to the output. At a time, any one of the input is connected to the output. Okay. When S1 equal to 1, B is connected to the output. Okay. And close this file. And next, run simulation, run behavioral simulation. You can see output in TCL console also. Okay. You can see the output in TCL console also. When A equal to X, B equal to X, S1 equal to X, Y1 equal to X. When A equal to 0, B equal to 1, S1 equal to 0, Y equal to 0. Whatever the A value is there, that is assigned to Y. If A equal to 0, B equal to 1, S1 equal to 1, Y equal to what? 1. Okay, you can see this outputs in the TCL console also, or in the waveform also you can observe. See here. Fit to page. So, see here, this one. When when A equal to 0, B equal to 1, and S1 equal to 0, Y equal to 0. Okay. And here when A equal to 0, B equal to 1, and S1 equal to 1, Y equal to 1. At a time, any one of the input is connected to the output. Okay. So this is the multiplexer code. Any doubts or queries? One second. Yeah, tell me. See that. Is it fine? Do you understood? Any doubts or queries in this? Waiting for your response. Do you understand this code? Test bench.
Yes, sir.
Okay. Yeah. Suppose a full adder is there. Okay. Like a full adder is there. Full adder. Um, so I think full adder you can. So this is logic gate behavioral modeling. So logic gate behavioral modeling means here you need to write by using if else statement also. Okay, if else statement you can write. Okay, and next uh, next full adder using behavioral modeling I will write. Okay, suppose here you need to add the sources. Okay, create the design source. So my design source is full underscore adder underscore behavioral. Okay, okay, finish. Okay, yes, full adder behavioral model. Okay, this is full adder behavioral model. Okay, first what you need to do? First you need to initialize the. So first you need to first start module. So what is my module name? Full underscore adder underscore behavior. Okay, behavioral modeling. I need to declare the input. Okay, input. What are the inputs? A comma B comma or here you write a comma B comma C in comma output output uh, output reg. I need to declare with reg data type no sum comma C out sum comma C out. Okay, and next always I'm using always at the rate star is nothing but implication operator. Okay, so if there any change in the input then it will be applicable for all inputs also. Okay, always begin. Okay, always at the rate begin. Okay, at the rate 1 second I will show the code. Always at the rate yeah you need to declare this one. Yeah, always at the rate begin. Okay, it should end with the semicolon. Sum equal to what? Sum equal to a xr b xr c in. Okay, and carry out equal to what? Carry out equal to I am using a and b or 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 next b and c. I am using bitwise AND gate and OR gate. Okay, b and c or a and a and c in. Okay, this is also c in and semicolon and next end c out a and b and b and c in a and b and b and c. One second, a and b and c in plus a and c in. Yeah, end. Okay, so I will save this code. So I saved this code. 1 second, syntax error I am getting. 1 second. Full adder underscore ab reg sum comma c out always at the rate begin end module. Okay, end module. Save this code. Yeah, save this. Okay, and next coming to the test bench. So I can use this test bench. What is that? This full adder data flow modeling is there now. So I can use the same test bench. So if you see the test bench, so just module full underscore tb where sum comma ca reg a comma b comma c. This is a connection by position or connection by name. Connection by position with order list no. Can you able to find out the difference between the connection by name and connection by position with order list? So this is full underscore DUT TB. So this is my instance name. Okay. And A B C some comma CA initial begin. I am giving all the cases like 0 0 0 0 0 1 0 1 0 0 1 1 1 1 0 1 1 1. Again random stimulus I am giving. I am running for 100 time minutes and dollar stop and ended in module. Okay. So here select all, copy this. One second. First I want to copy this module. Okay. Copy this and in the simulation sources you need to add the simulation, create, and you need to choose the location where you need to store this value and OK, finish. So uh, my module full underscore adder underscore TB I'm giving. Okay, my module name is full underscore adder underscore TB. Orders underscore TB. This is um, one second. This one, yeah, this I will close. Select all, copy this and paste in here. I'll change the module name as full underscore adder underscore BEH, behavioral modeling. Okay, in order to understand. Okay, and what is my design name? What is my design name? Full underscore adder underscore BEH and some comma CA and A comma B comma C. Okay, these are the range means internal variables of the test bench and I am giving the stimulus. Okay, so save this. Okay, I saved. Okay, see here. So full underscore behavioral. This design is instantiated. Design is instantiated. Okay. So if I want to see the means elaborated design, go to this design full underscore adder underscore behavioral set as top. If I want to see this simulation also, so this TB set as top. Right click and set as top. Okay, right click and set as top. I want to see the elaborated design. So this is how the code is converted into netlist. Okay, this is the full adder circuit. Okay, code is converted into netlist. Close this and so run simulation, run behavioral simulation, run simulation, run behavioral simulation. So in the TCL console, you can see the output. Why? Because you used a dollar monitor. No, I think TCL console you are not getting. Okay. So dollar monitor you not given. No, that's why you are not getting. Okay. So you do give the dollar monitor, you'll get in the TCL console. So I can see in the waveforms. Yeah, see here. So so when A equal to B equal to 0, so all are 0 only. Okay, just to zoom this. Okay. Yeah. When A equal to B equal to 0 0 1. Okay, 0 0 1 I am getting someone carry 0 and next 0 1 0 someone carry 0, 0 1 1 some 0 carry 1, 1 0 0 someone carry 0 and 0 1 1 1 0 1 some 0 carry 1. Next same thing 1 1 0 1 1 0 is some 0 carry 1, 1 1 1 someone carry 1. Is it fine? Do you understood how I am getting? How I am analyzing the simulation waveforms? Anyone give response so that I will move forward.
So you are checking every 10 nanosecond.
Yes, yes.
So is this because you put that number there?
Delay. Yeah,
Okay.
delay. Where is that? Full underscore TB. I given this delay. Last
Okay.
class we discussed about the inter-segment delay and intra-segment delay. So mostly we are using this is the inter-segment delay as default delays only. Okay, like these are the delays we are initializing in the test bench. Okay, you can use suppose in the test bench you can use at the rate negage of clock or passage of clock also. During this that also you can get the waveforms. In the place of delays, so you can use at the rate negage of clock, at the rate passage of clock also you can give. Means during the sequential circuit I will tell you. Mm. During the sequential
Okay.
circuit I will tell you. Okay.
Also, sir, this full adder I can write by two half adder. So,
Yes, yes. Structural modeling you can use.
okay.
Structural modeling you can use here. Uh, See full adder. Full adder using. I think I showed full adder using structural modeling. Just I will
Okay.
open this and I will show you. One second. Verilog programs. This is full adder using half adder.
Okay.
I'll open this project. Just I'll close this. Okay. So structural modeling. That means we are using two half adders and one OR gate. No. So first you need to write the code for half adder, and next you need to instantiate two times, and OR gate also by using gate level modeling you need to write, and test bench also you need to write. Okay. See here. This is the code. First I wrote for the half adder. This is the code for half adder. Okay. So half adder means assign. I'm using data flow modeling only. Assign sum equal to AX or B, and assign carry equal to A and B. And after that, I instantiated. So that is a module full underscore adder input A underscore FA, B underscore FA, output sum underscore FA, carry underscore FA. And internal variables are there, no, that I am declaring with wire data type W1, W2, W3, and half underscore adder I'm instantiating. This is connection by name or connection by position?
Name.
Name. Why? Because dot is there. Dot A. Whatever the variables outside the bracket are nothing but design inputs and outputs. Inside the bracket are nothing but test bench inputs and outputs. Okay. So you can draw that and how you are getting the inputs and outputs you can analyze. And here I am using assign carry underscore F equal to this is OR gate. Okay. You can see the elaborate design also. Okay. You can see the elaborate design also. Like that you can use you can write for half subtractor and full subtractor. See here. So I am getting two half adders and one OR gate. If you click on plus sign, this is one half adder. If you click on plus sign, this is one half adder. Is it fine? Okay.
Yes, sir.
Okay. Yeah. One more. So mm, have you gone through the adders in the digital? I think you are aware of digital. One second. Verilog codes. This is level 2. Level 2, this is encoder and decoder also you can write. Level 0. Okay. 3 to 8 encoder, 4 to 2 encoder. Okay. This is 4 to 2 encoder. I think encoder is not there. One second. Level 0 encoder, 4 to 2 encoder is there. Okay. So see here 4 to 2 encoder. This is the code for encoder. Okay. So encoder you have seen or not? Just uh, one second. So like we are getting the logic expression for encoder when you assign the encoder. So that is we are declaring the encoder. What are the how many inputs are there? Four inputs are there and one output is there. Okay, at a time any one of the input will be one and it will produce the output which is equal to the binary representation of that input. Okay, so input A, B, C, D, and output is y1 comma y2. Assign y1 equal to B and C, and assign y2 equal to C and D end module. Okay, this is 4 to 2 encoder, and this is also test bench. Okay, so test bench, just see here. So I'm declaring the this is test bench where y1 comma y2 reg A comma B comma C, and I need to instantiate connection by position. For every time units, I'm giving A, B, C, and value. Okay. Uh, do you know the encoder? No, you already studied in digital. Do you know or not? So just to go through that encoder means encoder working principle. Okay. So here I wrote the RTL codes. Combinational. I'm opening the combinational project. Opening the project. Okay, you make a project combinational. So whatever the combinational circuits are there, you can write there, or you can make one data flow modeling. Whatever the combinational data flow modeling are there, you can write over here. Okay, create the design source. What is my design source? Encoder. Encoder is my design source. Just copy this module name and create the design source. Okay, so file location same. Okay, finish. My module name is also same. So this is my encoder. Okay, and go to this GVim. Just select this, copy this, and just paste here. Save this. So I want to see the design. Set as top module, and go to the simulation. And so my TB is encoded TB. My TB file is encoded TB. Copy this, and so add the simulation. Create. So my test bench file. Choose the location. Select. OK. Finish. OK. Yes. So my encoder TB file is created. Encoder TB file is created. Next, go to this code. Select all. Copy. Next, paste here. Save this file. Next, I want to see the elaborated design. So right click and set as top. Simulation also you need to make as a top module. Whatever you are simulating and whatever you are elaborating, that you need to make as a set up top in design sources as well as simulation sources. Okay, so this is my encoder design. Okay, so B and BRD and CRD. This is my encoder design. And next, go to the simulation. Run behavioral simulation. At a time, any one of the input is 1, and that binary representation you will get at the output. Okay, so am I getting the, you see here, A equal to 0, B equal to 0, C equal to, Y equal to, D equal to 1 means Y equal to 1 1 I am getting. Okay, 1 1 means Y3. Y3 means what? What is the binary representation of 3? 1 1. No? So you will get the binary representation of output. Okay, so just see here. So here A equal to 1. So 1 means this is 0 0. Okay. So 0 0 you'll get 0 0. Let us take this is y0, y1, y2, y3. So y0 means y0 having the binary representation is what 0 0 no? Like that you will get. And similarly now b becomes 1. This is y1. So what is the binary representation for 1 0 1 no? Okay. And next 1 0. Okay, 0 0 at a time any one of the input is 1. Okay. So this is y2. Y2 is what is the binary representation of 2 1 0. You are getting 1 0. Okay. Similarly next uh, uh, d is 1, y3 is 1. So you are getting y 1 1. Okay. So like this you can design the photo to encoder and priority encoder also. Okay, that is your task.